Okay, so we're going to have a look at how to complete the square, and we look at some leaving cert higher level questions where completing the square has been important to you being able to complete the question. So the first thing to say is we complete the square on quadratic expressions. So in a second we will complete the square on this expression here. But you know, the general form of a completed square expression is a constant on x plus h squared plus k. If we can take a quadratic, manipulate it so that it looks like this, then minus h, you change the sign of the term in the bracket, and then k, you keep the sign of the term at the end of the expression, or the term that's been added to your bracket, and that would give you the turning point of this curve. So if this curve was n-shaped, obviously this would give you a maximum. If this curve was u-shaped, that would give you the minimum. Now when they ask the question, they'll use different letters. Like here I have hk, we'll see that one in a second. I've seen it with b and c here. This example here has a and b because there's no constant in front of the bracket, and we'll go through where it arises where there might be a constant, and in an example like this where there's no constant. So let's have a look. What we're going to do to complete the square is we have to make sure that the coefficient of x squared is 1. If it's not 1, we're going to have to do some factorizing first. We'll see that coming up. But in this example, the coefficient of the x squared term is 1, and so we can start with the rest of the process. Now the rest of the process is we write down the x squared term and the x term as they are, and then we take the x term, or the coefficient of the x, and what we're going to do is we're going to half that to give 5. I'm going to square it to give 25. So we half it and square it. We add a 25, and then we come past the 32, or where we're going to write the 32, and we minus a 25. And then the 32 that's in the original expression, we write that here. So we can see what I've written here in black is the original expression, and what I'm doing with the original expression is I'm adding and subtracting the same number to it, 25. If you add and subtract the same number, you're not exactly changing the expression, you're just changing the way that it looks. So the first three terms then can be factorized with the same terms in the brackets. So x squared plus 10x plus 25 is x and x, 5 and 5, a plus and a plus. And how we come up with the last term in each of those brackets is, it's just the term, the x term, when we halved it, that number will always be the number that's in with the x in the bracket. Okay, so that's the first three terms, give us those two brackets, and then the 32 minus 25, that gives us plus 7. And so in completed square form, we have x plus 5, and x plus 5 is x plus 5 squared, and then plus 7. And we can see that is of the form x plus a squared plus b, which is what they wanted. There was no number in front of the bracket because the x squared coefficient was 1. We'll see ones coming up where we have a number in front of the bracket. Now, it didn't ask it in this question, but just a couple of properties of this function. If I was to write this expression as a function, f of x equals x squared plus 10x plus 32. A positive x squared function is u-shaped. Okay, so it looks like that. It may or may not have roots. It might have 2 roots. It might have 2 equal roots, or 1 actual number root, or if the x-axis is down here, it might have no roots. But what we have found is we found the minimum point of this quadratic. So a quadratic function that has plus x squared is u-shaped. If it's u-shaped, it has a minimum rather than a maximum. And what is that minimum? Well, we take the bracket and we change the sign of the 5, so we make it minus 5, and we keep the sign of the 7. And so that's the minimum point of this curve, if that's what was asked. And we'll see in questions coming up that can be useful in terms of if we have a function and we want to translate it or move it somewhere else, having it in completed square form is a useful way to be able to do that. Okay, so that was asked back in 2008, and let's see a question where it may have been asked a little bit more recently. Well, actually this one is further away again, but the reason we have this one is this is very similar in the way that it was asked to something recent, and we'll show that on the next slide. So here we have a function. This is a cubic function. It's a plus x cubed, so it would go up first, and then it would go down, and it would go up again. What we're being asked to do here is we're being asked to find f prime x, so the derivative of this function. So we'll use the power rule to do that. So 3 comes down the front, the power goes down by 1, so that's 3x squared. 2 comes down the front and multiplies to give us 12x. 15, we drop the x, and then 36, the derivative of a constant, is 0. Now, that's the derivative, f prime x, and that stands for the slope of tangents to this function, or the rate of change, we could call it, rate of change. But what they've asked us to do, they've asked us to express the derivative in the form 3 on x plus a squared plus b. So they're asking us basically to write this in completed square form. So let's go ahead and do that, and the steps here are slightly more complicated than what we looked at, so let's come down and give ourselves a bit of room. If we don't have a 1x squared, or if the coefficient of x squared isn't a 1, we always start the completed square process by factorizing out the coefficient of the x squared. So in this case it's 3, and we have x squared plus 4x plus 5. So I've just divided 3 into each of these terms. So this is still f prime x, the derivative. We're just making it look different so that we can read information from it. The next thing we're going to do is that 3 out front has no effect for the next few lines on actually doing the completed square process that we did on the previous slide, which was writing down the first 2 terms, and then we take the x term and we half it to give 2, and we square it to give 4. So let's add a 4 and minus a 4, and then this 5 is obviously still here. So again, we've added and subtracted the same term, which means the original expression is still the same, it just looks different. Now, the 3 is still outside. The first 3 terms now, we can factorize to be x plus 2 on x plus 2, which will be a square in a second. And then plus 5 minus 4 is plus 1. So we have 3 on x plus 2 by x plus 2 is x plus 2 squared. And then I'm going to multiply, well actually let's just write down the 1 first of all. But finally what I'm going to do is I'm going to multiply the 3 by the x plus 2 squared. But then this latter term in the bracket, we have to get that outside of the bracket by multiplying it by 3. 3 by 1 is 3, and we can put that at the end. Now again, wasn't asked in this question, but what information can we read from this? We can read, this is a U-shaped function again. So the derivative of a cubic plus x cubed cubic function is a plus x squared quadratic function, so this would be the derivative of it. It doesn't exactly look like that. Let's probably write it a bit better. So, and what we could find is the graph of the derivative, the minimum value of it, can be found by changing the sign of the term in the bracket, which is minus 2, and keeping the sign of the term outside the bracket here, which is 3. So minus 2, 3 would be the maximum, or in this case, sorry, the minimum rate of change of the original function. So that was 2004, but it has been asked recently, which we look at in the next slide. Now, I did multiply this 3 in by the 1 to give plus 3. In general, that's how we write completed square form. This question didn't use the words completed square, and actually it kept the b inside the bracket. But it is good just to expand it like this. I mean, not in this question because they didn't ask us to. But in general, when we're completing the square, we expand it like this so that we can change the sign of the term in the bracket, and we keep the sign of the other one to read the minimum value or maximum value of the expression. Okay, so that was 2004. Here's the 2021 example. It's exactly the same. We have this cubic function. We are going to differentiate it to give us 6x squared plus 12x minus 12. And then they want it in the form a on x plus b squared plus c. And we can see that the c is indeed outside of a bracket this time. So the first thing we're going to do is we're going to factor out the 6. So this becomes 6 on x squared plus 2x minus 1. We look at the first 2 terms and we leave them unchanged. And we take the coefficient of the x and we half it to give 1. And we square it to give 1. So we're going to add 1 and subtract 1. So we can see it here. We're going to add 1 and subtract 1. We did that by halving the x number and squaring it and then taking that away. The first 3 terms, we can see them in green here. They're going to become x plus 1 on x plus 1, which is x plus 1 squared. And then minus 2 minus 1 is minus 3. And then finally, even though they didn't ask it for in the last example, it is asked for in this example, we have to multiply that 6 by that minus 3 to get it out, to give us minus 18. So if this is a cubic function, which goes up first and then comes down and up again, the graph of the derivative of that, so the graph of f prime x is a quadratic function, u-shaped because it's plus x squared, and the minimum point of this function is we change the sign of the term inside the bracket, minus 1, and we keep the sign of the other one, minus 18, and that would be the minimum point. Now in this question they asked us what is a, b, and c, so we just match it up from the expression that was given, and we have a is 6, a is 6, b is 1, and c is minus 18. Okay, let's have a look at another one. So back in 2017 they gave us this example. Now what's tricky about this example is just that there are fractions involved. When we do our factorizing in a second, we'll see that when we half and do the squaring, we'll have fractions or decimals involved, and it looks a little messier, but let's work our way through it. So the first thing we're going to do is we're going to factor out the 2. So we have f of x equal to 2 on x squared minus 7 over 2x minus 5. Now look, if you wanted to say 3.5x, 7 divided by 2 is 3.5, and we're going to leave it as a fraction. Now the next part is we write down the first two terms inside the bracket as is. We're going to take the coefficient of the x, which is minus 7 over 2. We're going to half it, that gives us minus 7 over 4. And then we're going to square it, which will be 49 over 16. So basically we're going to add 49 over 16 and we're going to subtract 49 over 16. So let's have a look at what that looks like. So we've added 49 over 16 and we've subtracted 49 over 16. Now, to get the bracket squared, all it is we took the coefficient of the x and we halved it. And that's what always goes in the bracket as the second term. That's just going to be x minus 7 over 4. So let's go and have a look at the next line. So that's 2 on x minus 7 over 4 squared. And then minus 5 minus 49 over 16. That's minus 129 over 16. And finally, the thing that we can sometimes forget, we have to make sure to be careful, is we need to multiply this 2 by the minus 129 over 16 to get it outside of the bracket and give it its proper completed square form. And so 2 times minus 129 over 16 is minus 129 over 8. Now, I'm anticipating that what they might ask now is this is a U-shaped quadratic, and I'm anticipating they might ask us what's the minimum value of this. All we do is we take the term in the brackets and we change the sign to give us 7 over 4, and we keep the sign of the other one. Now you'll note, we didn't mention it so far, but the number in front of the bracket has no effect on what the max and min is. If this was 4 on x minus 7 over 4 squared minus 129 over 8, it would still have a minimum value of plus 7 over 4 minus 129 over 8. A number in front of that bracket, that just narrows the function or widens the function, depending on what we do to that number, whether we increase it or decrease it. Okay, so what was the second part of the question? Well, it was indeed find the minimum point of the function. So all we have to do is, it's in completed square form, and the max or min is change the sign of the h, so minus h, and keep the sign of the k. And so we can see that that's 7 over 4 minus 129 over 8. Now, that's the completed square portion of the question done. We can use completed square to find the roots of f of x equals 0. We'll do that in a second, but let's see what else they might have asked in the question. So the C part 1 says, explain why the function has 2 real roots. So we know that this was a U-shaped function, and a U-shaped function will go up and down forever, and the minimum value of that function we know is 7 over 4 minus 129 over 8. So if that quadratic function is U-shaped, well then obviously if the y value is less than 0, minus 129 over 8, that means that the function or the curve dips below the x-axis. Not all functions do. We can have a U-shaped function that doesn't go below the x-axis. That's one where the roots wouldn't be real. But we can see because the y-coordinate is a minus number, well then obviously the minimum point is below the x-axis. And so if it's below the x-axis, there's 2 real roots. If that minimum value was 7 over 4 is 0, that would mean that it touches the x-axis and there would just be one real root. Okay, one root here, there wouldn't be two roots. The fact it's a minus, it dipped under the x-axis, there's two real roots. So that's one method to do it. The other method we could have done it is, we have the original quadratic expression, and if we take the discriminant of that, b squared minus 4ac, we can determine the nature of the roots. If the discriminant is positive, there's two distinct real roots. If the discriminant is negative, there's no real roots. And if the discriminant is equal to 0, well then there are two equal roots. So let's actually go ahead and do that. So a is equal to 2, b is equal to minus 7, c is equal to minus 7. Sub them into the discriminant, and we get the number root 129. Now root 129 is a positive number, and because it's a positive number, it means that we have two distinct real roots. So that's good revision in terms of what the discriminant can do for you. It can help you decide if there is two real roots, as is in this example, if there is no real roots, or if there is two equal roots where it touches the x-axis and the discriminant would be equal to 0. Okay, one more part to this question. I'll show two methods to do it, and so we're kind of can move away from completed square form if we want. If we just want to solve this quadratic equation, f of x equals 0, we have f of x, this is it. If we let it equal to 0, this is a quadratic. How do we solve a quadratic? Well, we can try brackets. Brackets don't work here, the factorizing, but we can use the minus b formula. If we plug in the numbers into the minus b formula, we get 7 plus root 29 over 4. We can split that up into 7 over 4 plus or minus root 29 over 4, and then we can say that that's 7 over 4 plus or minus the root of 129 over, we can change 4 into root 16, and then one of the rules is if we have root a over root b, we can say that that's the root of a over b. So you can put 129 over 16 under the same radical sign, and we have the answer in the required form. Now, I've kind of flown through that because that's not the preferred method to solve that equation, given that we have spent some time completing the square. But how do you solve any quadratic equation equal to 0? Well, minus b formula will always work. The only tricky thing here might be getting it in the required form, and this is the required form. Now, I don't know, if we go up here, it's worth testing. If you had put this into your calculator, no, you can't put plus or minus into here. Okay, so let's see how you can use completed square form to solve a quadratic. So in general, this isn't the preferred method, let's say, to use, but you can use this completed square form by letting this equal to 0. We won't have to use factorizing or the minus b formula to solve it. So let's see how we would do that. So the first thing we're going to do here is we are going to add a 129 over 8 to both sides. So that gets rid of it from the left and it adds it onto the right hand side. Next thing we're going to do is we're going to divide by this 2 that's in front of our bracket. So this is going to become x minus 7 over 4 squared equals 129 over 16. We're then going to get the square root of both sides. Now if we get the square root of both sides, the left hand side, x minus 7 over 4, will equal plus or minus root 129 over 16. And then what we're going to do is we're going to add 7 over 4 to both sides to get x is equal to plus or minus root 129 over 16 plus 7 over 4, and then we might just reverse the order of this to get it in exactly the required form. So it's a really interesting thing that we've done there. Like, we normally would never solve a quadratic equation by completing the square first, because there was a lot of work to complete that square or write it in completed square form. But the fact that we had done that work already, maybe it made sense to just let that equal to 0. And why does completed square form allow us to sort of do this different type of equation? Well, your original quadratic expression has two places where there's an x. There's an x squared and there's an x. Whereas when you write it in completed square form, we only have one x. And so it's quite easy to isolate that. Not easy to isolate it in the original formula. That's why we use the minus b. But when you have completed square form, you can isolate your x because there is only one x. So moving to a couple of real world type questions and where completed square form was needed or used in the question. The first one here is a question about a footbridge opened in Mizen Head. we can see the function here is y equals 0 minus 0.013x squared plus 0.624x. And that's a minus x squared coefficient, which means it's a quadratic that is n-shaped. I mean, we can see the shape of the bridge here. If it's n-shaped, it means that it has a local maximum, and we can find this maximum in two ways. One, we can differentiate the function, which finds its rate of change or slope, and the maximum is the x value where the rate of change or the slope of the tangent at that point is 0. So we're going to differentiate and let it equal to 0, solve for x. But the other way we could have done it, and we'll see it later on in this question, is we could have completed the square or turned this quadratic expression into completed square form. And when we had it done, we could read the maximum then. And we're going to do that, like I said, in a bit, and we're going to use it then to find something else in the question. But let's just work through the question, forgetting about completed square until we hit on it. So how do you find the highest point of the arch? We're looking for the highest y value. The highest y value here is occurs where this curve is at its maximum. We find the maximum by differentiating the function and letting it equal to 0. So we're going to use the power rule. So 2 comes down the front and multiplies by minus 0.013 to give us minus 0.026x, and then 0.624x becomes 0.624. So we drop the x when we're differentiating it. Now we're going to let this equal 0, and what I'm going to do is I'm going to add 0.026x to both sides. I'm going to divide both sides by 0.02x, and I figure out that x is equal to 24. And that kind of makes sense. This curve is symmetrical. We have an x value of 0 at the start, and we have an x value of 48 when it hits the x-axis again. Makes sense that the x value of the maximum is 24. Now we need to find the y value. The y value represents the height of the bridge, so we just sub the 24 back into the original function, and when we do that, we get a y value of 7.488. So this point up here, so is 24, 7.488. Like I said, we're going to see this later on. This 24, 7.488, we're going to see when we complete the square with this expression. So it's just linking what we did in the previous questions with this one here. Okay, so that's the answer to that question. The highest point is 7.488. Now, the next part of the question, it says that the perpendicular distance between the walking deck, so we can see the walking deck goes from D to E. If we look at it on the picture on the previous slide, so here's D, and it goes over to E here. So that part of the walking deck is 5 meters above AB. Okay, so this measurement here is 5 meters. We can see the point at the start here is 0.5. That means that this line that goes through DE is called y equals 5. That's the equation of that line. Horizontal lines are called y equals k, where k is the y coordinate that they pass through. Okay, so the question is, what's the coordinates of D and E? Well, if we let our quadratic expression equal 5, so the y value is 5, let's sub 5 into the quadratic expression that we have, and then we're going to solve for x. So how do we solve for x? We are going to do a quadratic equation, so I'm going to collect all the terms on the left. I can see that this is probably going to be a minus b formula type question, where a is 0.013, b is minus 0.624, and c is 5. So we'll pop them into the minus b formula. And it says give your answers to the nearest whole number, so this rest of this question is sort of an estimation. But one of the values, the d value, is, let's say, 10.15, which we're just going to call 10. So that's d is 10.5. And then the e point is 37.8. We round it to 38. So that's 38.5. So that's the coordinates of d and e, correct to the nearest whole number. Okay, the next part of the question asks us to find the area of this shaded region. Now, the region in the middle here, I mean, that's going to be simple. That's just a rectangle where the x-coordinate here is 10, the x-coordinate down here is 38, so it's 28 wide, and it is 5 high, so 28 by 5 is 140. So that's going to be really easy to find when we get to it. But the part that's difficult to find in this question is the area between the curve, let's say this curved line that goes from A up to the point D here, between the curve down to the x-axis. And how do we find the area between a curve and the x-axis? Well, we use integration. So we're going to integrate this blue area here. This is symmetrical, so we're going to just double it for this other area. I mean, we could integrate the function from E to B as well, but there's no point. It's symmetrical with this point A to D. So we're just going to double it. And then we're going to find the area of the rectangle in the middle. Okay, so let's go and integrate the function. So we're going to integrate the function minus 0.013 x squared plus 0.624x from x equals 0, which is here, to x equals 10, which is here. Okay, so when we integrate the polynomial like this, we increase the power. So it becomes minus 0.013x cubed, and then divided by the new power, so divided by 3. And then plus 0.624x squared divided by 2. So 10 and 0 are the limits of integration. Remember, the 2 is just because it's symmetrical. That represents this other blue area on the other side. When we sub in 10 and 0 and tidy it up, we get 2 times 26.87. So each of these blue areas is 28.87 multiplied by 2, and we get 53.74. The rectangle, as we said, was 28 wide, multiplied by 5, which was 140. And so the total area of that shaded region is 140 plus 53.74, which is 193.7. So a little bit of integration. Integration is the only real way that we have of accurately finding the area between a curve and the x-axis. And then obviously the rectangle in the middle was just simple. We could have, if we wanted to, integrated the line y equals 5. So we could have integrated 5 dx from this coordinate was, x coordinate was 10 and this was 38, from 10 to 38, and we'd have also got 140, but just kind of looked simpler just to find the area of a rectangle. Okay, and sorry, always read the question again. It says correct to the nearest whole number. You don't want to be giving away marks, so 193.7 rounded up and we had 194 meters squared. Okay, so using what we learned in part D, we want to write down the equation of a parabola for which the coefficient of x squared is minus 2. So the coefficient of x squared is no longer minus 0.013, it's minus 2. The x value of our other maximum was 24, now it's going to be 3, so we replace the 24 with a 3. And the y coordinate was 7.488, and it's now minus 4. So we're going to replace the 7.488 with a minus 4. And remember that a minus by minus is plus, so y minus plus 4 rather is minus 2 on x minus 3 squared. And that's the equation of a different parabola that has a different maximum, obviously, and where the x squared coefficient has been changed, that narrows or widens the function that we had. So it's shifted it lower, it's gone from 7.488 down to minus 4, and then it's also narrowed or widened it because the coefficient of x squared has changed. Okay, so in this real world question we have been given a path that follows a quadratic function, so minus 0.274x squared plus 1.193x plus 3.23, and we can see it's a minus x squared function, so we knew that it was going to be n-shaped in nature, and that's obviously shown by the graph. And the ball has left the hand at point A, and we've been given the coordinates of that, and then it has entered the basket later on at point B, and we've also been given the coordinates of that. So the first part of the question is to find the maximum height reached by the center of the ball. Now, we're looking at completed square form. We know that completed square form can find maximums given quadratic functions, but I think we'll just use calculus first, because that would be the go-to if you were asked this question. Like, it's just easier and a shorter method, especially given all the decimals in the question. So what we're going to do is we're going to differentiate the function, so using the power rule. So we get minus 0.548x plus 1.193. The constant, when you differentiate it, goes to 0. And then what that gives us is the rate of change of the height of the basketball. We're interested in the rate of change at the maximum, and the rate of change at the height at the maximum point is 0, or we can say that the slope of the tangent to the function or to the curve at the maximum is always 0. So we've differentiated the function. We're going to let it equal to 0 now to see what x value that is. We're going to add 0.548x to both sides, divide both sides by 0.548, and we get x is equal to 2.177. So a quick common sense check. I mean, if we map down to the x-axis from what it looks like is the maximum point, it looks like 2.177 is a valid answer. It asks us to find the maximum height. We have the x value where the maximum height occurs. We need to stick that x value back into the original function. So we sub it back in, and we get that the height is 4.529. So this point here is 2.177 and then 4.529 meters high. Okay, so that's that. We could have done that question by completing the square. So let's go and look at how we would complete the square, which is obviously the focus of the lesson. We write down our function. We can't complete the square unless the x squared coefficient is 1. So we need to factor from the 3 terms minus 0.274. So we're going to divide that into the 3 terms. And when we divide it into the first term, obviously we get x squared. And then if we divide it into 1.193, we get 1193 over 274. And if we divide it into 3.23, we get 1615 over 137. When we complete the square, remember, we concentrate on the first 2 terms. We are going to take the coefficient of x, we're going to half it, so we're going to divide that by 2, and we're going to square it, and then we're going to add and subtract that. So let's see what that looks like. So we're dividing 1193 over 274 by 2 to give us 1193 over 548, and then we're adding that, we're squaring that, and we're adding that, and we're subtracting that. And the minus 1615 over 137 is still in the question. So we haven't altered the function other than to just make it look different so we can complete the square. When we're finding what goes in the bracket with the x for the square part, it's always half of the x coefficient. So it's going to be minus 1193 over 548. So we know that that's going to be the squared part, and then we're going to subtract these from each other and see what we get. So we have minus 0.274 on x minus 1193 over 548 squared minus 16.528. So when we have minus 1615 over 137 minus 1193 over 548 squared, we get minus 16.528. Always remember to multiply the coefficient outside of the bracket by the latter term here, the last term, and that will get it outside of the bracket. And we have minus 0.274 on, now I've just written this 1193 over 548 as a decimal, 2.177, and then minus 0.274 times 16.528 is 4.529. And what do we notice? We notice that if we change the sign of the term in the bracket, we get 2.177, which was the x coordinate of the maximum, and we keep the sign of the latter term, which is 4.529, and that's the y coordinate of the maximum point. Now, we'll need this later on. We could have done this first part just with the calculus, but it was worth seeing that completely the square form could do it as well. Okay, the second part of the question says, find the acute angle to the horizontal at which the ball entered the basket. So here is where the ball entered the basket. Here is a horizontal, and there are 2 angles made when the ball enters the basket. There is this obtuse angle, and then there's this acute angle, and we're looking for the acute angle. So the way that we find that is, we want the slope of this tangent, so the slope of the tangent to the curve at the point B where it enters the basket. To find the slope of a tangent to a curve, we differentiate the function. So we differentiate this function, which we did previously in the first part. And what we're going to do is we're going to sub in the x value of point B. We want to know the slope at the particular point B, not at a point earlier on. We don't want the at the maximum. We don't want it early on in the question. We want it at point B, and at point B the x coordinate is 4.5. So we sub in 4.5, and we get a slope of minus 1.273. Now, when you're given the slope of a line to the horizontal, we can turn that slope into an angle by using the tan function. So the tan of the angle is equal to minus 1.273. Now, it's always, when we use a line, and we say the tan of an angle is equal to a slope, it's the angle it makes with the horizontal here. So the positive sense of the x-axis. So we want to find that alpha. They will then take it away from 180 degrees, and we'll get what theta is, the acute angle that's made with the tangent where the ball goes into the basket. So we're going to say the tan of the angle is equal to minus 1.273. Remember, it's this angle here. And we can use the cast method here. Like, we won't go through it in this example because we're concentrating on completing the square. But if you were to use the cast method, we have A, S, A, C, T, S. So that's it there. We have a negative tan. So tan is a negative slope. So tan is negative in this quadrant and in this quadrant. We can obviously discount this angle down here. We find the tan inverse of the positive version of 1.273, and that gives us 51 degrees, roughly. We'll do it exactly in a second. Let's say it's 51 degrees. That means that this alpha angle is 180 minus 51, which is 129. So alpha is 129, and as we've seen, theta is obviously 51. So using the cast method, we can figure out the alpha, and when we have the alpha, we can obviously figure out the theta, which is 51 or 52 degrees. Okay, so in this second part of the question, we're told that Sarah threw the ball again. This is her second throw. This time she threw it from a different place. She threw it from 0 to this point C. The curvature, let's say, or the curve of the function is exactly the same as the original function. It's just that it's been translated. It was thrown from a different place, but it has the same shape as the original function. It's just obviously started at a lower point. We're told that g of x is the image of the graph of f of x under the translation that mapped A to C from where she threw the ball originally to where she threw the ball the second time. The function follows that same, let's say, mapping. We can use this idea to find then the maximum height of the g of x function. Like, what was the highest point that she got with the g of x? We know that the highest point she got with the f of x was, let's write it down here, 2.177, 4.529. The g of x function is a translation of the f of x function under the image A to C. So let's see, how did A move to C? And then let's move the maximum of f of x in the same distance and direction, and that will give us the maximum of g of x. Hopefully that makes sense. So A is the point minus 0.5, 2.565. How was that mapped to 0, 2? Well, the x coordinate went up 0.5 and the y coordinate went down 0.565. So if we make those two changes to the maximum point of f of x, we should get to the maximum point of g of x. So we're going to take 2.177 and we're going to add 0.5 to it. That gives us 2.677. And then we're going to take 4.529 and we're going to subtract 0.565 from it. And that gives us 3.964. Now, anytime they say, show something, we don't want to use what they've given to us in the question. We want to actually do the maths ourselves and end up with what they wanted us to prove, which we've done. The maximum of g of x is 2.677, 3.964. Okay, the last question asks us then to find the equation of this parabola. Well, these two functions are the same shape, they're the same curve, they're both n-shaped, they just have different maximum points. And so this is our original function, and we earlier on completed the square. Minus 0.274 on x minus 2.177 squared plus 4.529. We can see the maximum, 2.177, 4.529. All we're going to do is we're going to take out those two values for the x and y coordinates of the maximum, and we're going to sub in the maximum that we just found in g of x. Now, even if we didn't find it, they had given that to us, and we'd be able to sub it in. So the equation of g of x is as simple as minus 0.274 on x minus 2.677 squared, the x coordinate of the new maximum, plus 3.964, the y coordinate of the new maximum. Now, it doesn't say what format they want the equation in, but if we were to square this out and tidy it up, simplify it, we would get minus 0.274x squared plus 1.467x plus 2. Okay, so hopefully that's given people a better understanding of, one, how to complete the square initially with x squared coefficients that were just 1. They're very easy to do. Then progressing through more complicated versions, and then obviously these tricky versions where we have decimal numbers. The principle behind all of them is the same, and what does it allow you to do? Well, essentially it allows you to read quite easily a minimum or maximum. It also allows you to solve quadratic equations in a different way, and probably most importantly and least observed through the examples in the papers is it allows you to do translations like the one we just saw here.